The random effect experiment is similar to the fixed effect experiment. The main difference is that we are not interested in inference about the specific levels that we chose to study. We only use these as a way to get a sample of levels to make inference about the entire population of levels. These are called random effects because they are supposed to represent a random sample of all possible levels of the factor. This does not necessarily mean that we are actually selecting these levels at random. Also, you can distinguish between a random of fixed effect situation by asking yourself, if we ran this experiment again tomorrow, could the levels change? You will also notice that most random effects are qualitative in nature. Here is an example. Based on this scenario, the batches would be a random effect. This is of course because if we were to run this experiment again, the batches chosen would not be the same. This scenario still represents a random effect situation for operators, even though we only have a set number of operators. It is random because we let those operators represent the population of all operators that may run the process in the future. You should realize that since this effect is random, that we are interested in not only the error variability, but also the treatment variability. If the treatment variability is large, then we need to increase the number of levels selected so that the estimate of the variability will be adequate. Think about this as if we are dealing with the variability of the mean. If the variance is large, then to get the standard error of the mean to be something manageable, we usually try to get the sample size as large as possible since SE x bar equals S/SQRT(n). In this case, the denominator is based on the number of factor levels. Here is another example. You should realize that this is a random factor because we are taking a sample from a large number of looms. Also, that if we ran the experiment again, there is a good chance that we would not choose the same looms. Note here that a random factor doesn't necessarily mean that we choose those levels at random per SE. Of course, that would be the best way to do it. Here is the model. Notice that it is similar to the fixed effects model. We will indicate the factor by a capital Roman letter, in this case m. Notice that the factor is a random variable, so it has a distribution. Also, notice that the errors are independent of the factors. Notice that not only will the observation vary from one experiment to the next, but the factor levels will also. You should realize that the only difference in adequacy checking is that we need to check for the distribution of the factor levels. We need to figure out the distribution for y based on our new assumptions. As you go through each line, make sure that you understand how this works. Notice that this means that any two observations in the same treatment group are correlated. Any two observations from different treatment groups are independent. Since we are not interested in specific levels of the treatment, we will estimate these variance components and make inference on them as we would for the means in the fixed effect case. Luckily for us, the estimate for the within variation is still the MSE. You should note that the MSE is not the estimate for the variance of the y's like it is in the fixed case. The EMS are more useful in the case of random effects. Of course, we have seen this result before in the fixed case. Now it should be noted here that the EMS for the treatment is similar to that of the fixed case since it is sigma square plus some function of the what we are interested in estimating to represent the treatment. In the fixed case, it was the sum of the tau's. In this case, it is a function of the variance component for the factor. We will use what is inside the brackets to estimate the variance component. Note again that this is not MS for treatment. Based on the method of moments estimator that we use for the variance component, it is actually possible to get a zero estimate for the variance component. Of course, this most likely means that the variance component is zero. This is just the percent of the overall variation represented by the treatment. Here are the results from our loom experiment. These are the calculations. You should understand how these numbers are found. Notice that the test is one-sided. This is because we cannot get a true negative variance. Based on the EMS, we need to decide how to create the test statistic. The fact that the ratio should be near 1 if the null is true lends itself to our decision for a one-sided test. How do we decide if under the null the ratio has an F distribution? Also, what should the DF be? We know that the ratio of two independent chi-squares over their DF follow an F distribution. This is the same for the fixed case. Here are the results for the loom example. Based on the small p-value, we conclude that the variance component is most likely not 0. Here is another example. We will use both SAS and Minitab here. Here are the results. Based on the Minitab output, we should reject the null. The variance component for flavor and error respectively are 7248 and 6782. The intraclass correlation is 0.517. This means that over 50% of the variation in melting speed is due to the choice of flavors. Here is the program to do this problem in SAS. Here is the ANOVA output. Here are the estimates of the variance components. The sample size can also be determined before an experiment is run. This can get more complicated than the fixed case because we can use this to get n, a, or both. Notice that we are still calculating lambda, then using it to get an f-stat. We define the type 2 risk and adjust only by dividing our critical point by lambda. Notice that this is different than what we did for the fixed effect case. This is another iterative process to find power. Of course, I have written a function in R to do this for you. It is in my courses under sample size, random. The function is called sample.lambda. Here is an example. Notice here that a is fixed. Here are the calculations for n equals 2. Here are the results of the function up to n equals 10. Notice that this is not larger enough. Once we change the endpoint to 20, we find that the desired power is reached at n equals 15. If this is too large, normally people will try to increase a to offset it. Now we can also use that increase in the standard deviation approach. Calculating lambda here is a little more complex based on the brackets and such. Once again, I have created a program for you. It is also in the sample size random file. It is called sample.percent. Here is an example from the ice cream experiment. Notice again that a is fixed. Again, 10 is not enough. We actually need n equals 64 to reach the desired power. Again, if this is high, consider increasing a. Not knowing makes the situation more complex. It also increases the amount of trial and error needed.